we are going to talk about double integrals today. So, well, recall from last time that I told you that this chapter we are going to learn double integration. So we're gonna follow topics from the book. So which is section 15.1, 15.2, 15.3, and 15.4. Basically, you're gonna learn how to set up the integration in two dimensions. Well, as I told you last time that we need to know how to graph the function. Well, because it's gonna be essential for this chapter. So well, you need to know how to graph the function. That's the first one. The second one, you need to know, you need to review how to do basic integration in one dimension. Well, first of all, before we start doing double integration, I am going to give you a review from calculus 1 because you know this is long time ago that you learned like in calculus 1. So let's do a quick review on integration and see if you remember it from the previous class. So in calculus 1, when you have a function y equal to fx, suppose that I have a function y equal to fx, and suppose that I know that my fx is greater than or equal to 0. So my function is going to be the one that I have here. Well, I'm going to use my highlight, the yellow highlight here. This is going to be my function f, which is the function is now above the x-axis because it is positive all the way, right? And well, what does it mean by integral of f from a to b? Well, if I add one more adjective, definite integral. So what does it mean by definite integral of f from x equal to a to x equal to b? Well, this means the integral, the meaning of the integral, this is the area under the curve, right? The area under the curve y equal to fx from x equal to a to x equal to b. So the meaning of integrals that you learn in Cal 1, the meaning is the area under the curve from x equal to a to x equal to b. X equal to a is here that I circle, x equal to b is here that I circle. So if you want to find the area under the curve above the x-axis, well, I should say here above the x-axis from a to b, this is the integral of f from a to b. Well, in calculus 1, when you learn integration for the first time, well, you're gonna learn the concept of something called Riemann sum. Well, Riemann sum. Well, what does it mean by Riemann sum? So Riemann is a mathematician who introduced the concept that, well, if you want to find the area under the curve, why don't you chop the area into small pieces? So the idea, he said that, he claimed that if you start from x equal to a, right, to x equal to b, well, we can compute the area under the curve by just chop the area here, you know, separate it into small pieces. Let's say you're gonna separate it into n small pieces. For each interval or each piece here, you're gonna have the width delta x. That is his idea. He said that, hey, if you want to compute the area, why don't you say that you're gonna use delta x to be the width of each box, and then you just multiply the width with the height. So the height for each box, we're gonna just, let's say we're gonna pick the middle one. Let's say we're gonna pick the middle one to be, you can follow my, you know, my pen in the red pen here. So I can pick the midpoint of the interval, and then I create a box here. I can pick the midpoint here, and then I can create a box. I can pick the midpoint here, and then I can create a box. You can see that after I do that for all interval here, I just pick the midpoint here, and then I create a box with the height equal to the point that I pick. So I am going to get the area under the curve, but it's going to be off a little bit because, well, the box that I create here, it's gonna, on some interval, you're gonna get more area compared to what you want. In some box, you're gonna get less area compared to what you want. But overall, it's gonna be okay, right? It's gonna be a good approximation. So Riemann say that, well, we're gonna use delta x, and then we're gonna multiply with f at the point x star. Well, the point x star is the point that we pick in between the interval there. So let's say here I'm gonna pick my x star here. So I pick x star, right? For each box, I pick x star here. And then, well, I am going to compute the area for each box. That means I'm gonna compute width times height, which is going to be delta x times f x star. And then after that, I put summation. So I sum it all for every box. So it's gonna be x subscript I from 1 to n. And this is called Riemann sum. And Riemann say that, well, if we take limit when n go to infinity, so this means you chop the area like to n pieces, and n is going to infinity. That means you chop it to infinite pieces. So at the end, when you chop it to infinite pieces, so your width gonna be just, very, very small, and it doesn't matter x star. I mean, it doesn't matter what the x star you pick, because at the end you're gonna get just the line, right? Because you chop it into infinite pieces. So at the end, your approximation is gonna get better. And well, when n go to infinity, it is going to be your area under the curve. That is the idea of Riemann sum. And you can see from calculus 1 that, hey, this is Riemann sum, and we call this Riemann sum. When you take limit already, it's going to be integrate from a to b fx dx. But you can see from calculus 1 that when we learn cal 1, no one use Riemann sum because it's going to be tedious, and it is ridiculous that you're going to do Riemann sum all the time. So we have better way to compute it, because the Riemann sum is so tedious and messy, so hard to compute. In 18th century, I think about late 18. So mathematicians, they discover something called fundamental theorem of calculus, and then they can use fundamental theorem of calculus to compute integral. So the Riemann sum, this is the traditional way to compute integral, but today we try to avoid it because it's so tedious. So the way that you always use, you're going to use fundamental theorem of calculus instead. This is fundamental theorem of calculus. So the way you compute integral easily, you're going to use the fundamental theorem of calculus. So from fundamental theorem of calculus, if you want to integrate a to b fx dx, well, you can say, hey, if I know that integrate fx dx, if I know that it is go to capital Fx dx, well, I can just integrate small f first, so I get capital F, and then I evaluate at x equal to b minus evaluate at x equal to a, and that's going to be fb minus fa. This thing that you use all the time in calculus 1 here, this is fundamental theorem of calculus. Thanks for mathematicians who discovered this thing, because once we discover fundamental theorem of calculus, we're going to use this thing all the time. So we can skip doing Riemann sum. Back to 17th century, if you don't have fundamental theorem of calculus, you have to use Riemann sum to compute the integral, which is super tedious and messy. Does it make sense? Well, the way that we're going to learn in this class, well, we're going to use fundamental theorem calculus. So that means you have to memorize the formula. This is the formula that I told you on Monday that you have to memorize. But I told you that you have to memorize number 1, number 2, number 3, and number 4. Number 5 to number 11, if you have to use it, I will give it for you. So no need to memorize here. Well, if I want you to use this thing, well, I'll give it to you because I want to test you how to set up the integral. I do not want to test you on your memory. It's, it is not fair for those of you who are not expert in Cal 1 and, well, I will give you the formula, except integrate constant, integrate x to the r, integrate cosine, integrate sine. This one you have to memorize. And also integrate 1 over x, log x here. This is going to be log absolute x plus c. I told you already that the special case when for number 2 here, when r is equal to -1, you cannot use this formula. Well, because when r is equal to -1, you have to use this formula, 1 over x. Oh, sorry, this is 1 over x dx. You get log absolute x. Sounds good. And another one that you're going to see it all the time is integrate e to the x. You get e to the x plus c. Well, 6 formula actually. 6 formula here, you have to be expert on it because I can ask you how to integrate these 6 formula that I highlight in light blue. But other than that, you're going to have a formula. And no integration by parts, no partial fraction, no, the complicated one, no more. Because we're trying to ask you to set up the integration, not the technique of integration. Does it make sense? Which is good for you, though, because, good for you because the technique of integration, those topics, they are so tricky. But, well, from here, we are going to do something that is not tricky. If you understand the process, you should be able and comfortable to do this. Well, one thing that you have to keep in mind, last time I told you about the substitution rule. The substitution rule from calculus 1, you have to recall this thing because I use it all the time. Well, let's say last time I said that if you integrate like 2x plus 1 to the 6th power dx, for example, well, I do expect you to do this integration by using substitution. So if you plan to expand the 6th power, that is not the way I want. The way I want you to do is, hey, I want you to do this. Well, for those of you who know that you are so weak in integration, you should start by let u equal to 2x plus 1. Chain of variable, and then you're going to get du equal to 2 dx. Well, this comes from du by dx equal to 2, right? And then it is similar to du equal to 2 dx. And then that means you can replace dx by du over 2. And then that means when you integrate this thing, integrate 2x plus 1 to the 6th power dx. So you're going to get integrate u to the 6th power because I replace 2x plus 1 by u. And then dx, I'm going to replace it by du over 2. You can see that by doing this thing, so you can integrate it easily to be 1/2 times u to the 7 over 7 plus c. And at the end, you're going to get 1 over 14 2x plus 1 to the 7 plus c. That is how you integrate it. I mean, by using the substitution rule. This is for those of you who want to go slow. If you know that you are so weak in integration, you can go slow like this. But when I do in class here, I'm going to do a little bit faster. Well, what I mean by a little bit faster is, well, this is too easy. So what I'm gonna do in this class, so I need to review this thing first because you need to follow me, right? And then this is the way I am going to show in class. So 2x plus 1 to the 6th power, what I usually do is, since I am going to pick u equal to 2x plus 1, I'm going to switch x here to be d to x plus 1. Well, when I say that, it means, hey, when I write this notation d to x plus 1, it means I pick u equal to b to x plus 1. And then after that, well, because I have to differentiate to x plus 1 with respect to x one time. So I get 2 here. Does it make sense? This is comparable to the thing that I just did before, u to the 6 du over 2. The same thing, but I just do it one more step quicker. So I just say that u is equal to 2x plus 1, and then I can just skip step to write everything, just, compress it to just short notation like that. And then now I can integrate more. So it's going to be 1/2. So you can imagine that you have integrate something in green to the 6th power d something in green. Well, it's going to give you that thing in green to the 7th power over 7 and plus c. Well, this substitution rule, if you feel like, hey, I do not understand, Ajahn, well, it's going to be your task to review that thing. Because when I do integration in 2 dimension, I'm going to go like this. So if I do, well, if the problem reduce to 1 dimension, I will do the trick substitution rule like this all the time. Sounds good? All right, that is how we do the basic integration from calculus 1. All right, so far so good. All right, next we are going to talk about double integration. All right, so it's 10:20 now. So let me give you the idea of double integration in 10 minutes, and then we're gonna do example. Okay, so please stay with me 10 minutes here. So I'm gonna give you the concept of double integration. It could be hard because this is the theoretical thing. I'm going to talk about how to generalize the Riemann sum into 2 dimensions. Well, if you can follow that, good. If you cannot follow that, that's still fine. Because this is just the theory part. Well, after we complete the theory part, we're going to do example together. Well, for those of you who know that you are super weak in calculus, well, all you need to know is you should be able to do examples. You don't have to be worried about the theory, but I don't want to just jump to example without talking about the theory. So I'm going to spend 10 minutes to talk about the theory. Well, this part, this is my warning. This part may be a little bit complicated for some of you, but well, we have to talk about the theory a little bit. All right, so well, the idea of the Riemann sum in 2 dimensions is, well, you know that the function of 2 variables is f(x,y), right? And this thing I told you already, this is a surface in 2 dimensions. So if you plot f(x,y) in 3 dimensions, you're gonna get the surface like that. Before, in 1 dimension, fx, you just have a line. When you have a line here or a curve, well, the integral means the area under the curve from A to B. This is the meaning of the integral. Integral from A to B, fx dx. Well, in 2 dimensions, when you have fxy here, you're gonna consider this thing in the plot of 3 dimensions, right? And then you have a surface here that I highlight in green. So the integral over rectangles gonna be the volume. So actually, what are you trying to do is you're trying to compute the volume. This is the volume, you see that? Over the region R. So actually the double integral that you compute here, fxy, dx dy, the thing that you're gonna compute in the next 10 minutes from A to B, from C to D here, this is going to be just the volume under the surface. It is a generalization from 1 dimension. So instead of area here, now you look at the volume. Because you add 1 more dimension to it, it's going to be the volume. And how to compute the volume? So the idea is, well, to compute the volume here, you can imagine that you have a base here that I highlight in yellow here. The thing that I highlight in yellow are here, this is a base. So before, when we compute the Riemann sum, we chop the interval AB to n pieces, right? So on slide page 6 here, we have the region R that I highlight in yellow here. This is the region R that I highlight in yellow. So we're gonna do the same thing. We're gonna chop it into n pieces. However, because this is 2-dimension, I have the region R. We're gonna chop it both x-axis and y-axis. So we get, chop it into small pieces, both on the x-axis and the y-axis. So you get that. And then the idea is you're trying to compute the volume for each box here first. Each box here, just trying to compute the volume each box here. And then once you get the volume for each box here, you can just sum it up, and that is going to be your Riemann sum. Sounds good? This is the formula for the Riemann sum, actually. Interesting, huh? So you just get this thing, like this box, like every box, and you can see that if you're trying to get the exact value of the integral, you have to chop the base here infinitely, right? From n pieces, if you take n go to infinity, you chop it infinitely. At the end, you're gonna get the volume. So the box, the length and the width of the box gonna be smaller, 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 and at the end you're gonna get just a line. And then once you add them up, so you're gonna get something that is smooth, and that is your volume, and that is the Riemann sum in 2-dimension. The text here that you see in slide 5, 6, and 7, the text here, I just copied from the book. If you want to look at how to express it in math notation, you can look at the book or slide 5, 6, and 7 here. Well, because you are not a math student, so I know this is maybe too much for you to look at the complicated formula at this point. So we are going to just give you the idea of the Riemann sum, and I will teach you how to do the examples and computation first. And if you can compute double integral, then you can come back to the theory after if you want to dig into something in more details. Well, this is the idea. So let's see. For example, you have c equal to 16 minus x squared minus 2y squared here. So basically you get the surface here that I highlight in light blue, like in green here, sorry. Well, the idea is if you want to find the integral of fx here, you're gonna need to compute the area under this surface from A to B and from C to D. However, well, I call that thing the base that I highlight in yellow here, I call that thing R. So you can see that the idea of the Riemann sum is that, well, if you chop the x-axis into 4 pieces and you chop the y-axis into 4 pieces, so you're gonna get like a 16 box here. I mean 16 pieces on the base here, and then after that you just compute the area of the box, right? You're gonna get 16 box, and then you get the area of 16 box here. You sum it up, you get 41.5. If you see that if you separate the base to 8 times 8 pieces, so this is going to be 64 pieces, 64 box. So you're going to get V, the volume equal to 44 plus 875. If you do more and more and more, so the value of V is going to get better, and then you're going to get the approximation that get close to the exact value of the integrals. Does it make sense? Well, but in real life, we are not going to just chop the base to n pieces and just add them up. Because in real life, we are going to take m and n, go to infinity, and then we're going to use the fundamental calculus. But the idea before you do that, this is actually from Riemann sum. Does it make sense? Well, hopefully some of you can follow that thing, but this is the idea or the theory of the double integration. So the notation gonna be like this. So when you do the notation for double integration, you're gonna put the function in the middle, and well, dA here means is you integrate with respect to the area here. So you need to put dA or dx dy here. So you can put dx dy or dy dx. It's just a notation. And then your double integral, you're gonna make the sign, integral sign here 2 times. And then that means you refer to double integral. All right, so let's look at how to compute double integral by using the fundamental theory of calculus. So again, this is similar to what I told you last time. If you integrate fxy dx dy, here if you use dx first, well, when dx is inside here, it means you use dx first. So you have to look at the x and you see if x is well, if x is inside here, so the boundary of x is gonna be inside too. So you're gonna integrate with respect to x from a to b, and then dy here you're gonna integrate y from c to d. This is going to be the notation. This is going to be x from a to b, and y from c to d. And a, b, c, d is just constant. So you can see that at the end, you're going to get x from a to b, y from c to d, right? And that is the box, the rectangle. So you can integrate that. And then when you integrate with respect to x first inside, you have to, how do I say? You have to, when you integrate with respect to x, you keep y as a constant. When you integrate with respect to y, you keep x as a constant. This is similar to differentiation. Sounds good? Well, I'm going to show you how to do that in a minute. Well, we already did example last time, but we're going to redo it again because this is your first class for double integration. I want to go slow to just make sure that everyone is on track and everyone can do this integration. Sounds good? All right, so, well, we're going to stop the theory part. We're going to look at example now. Well, as I promised you, those 10 minutes, it's just the theory part. So if you feel like, hey, Ajahn, I'm so interested in calculus, you can go back and look at it. And if you want to dig into more theory, email me or talk to me. I can make a section of, deeper in theory for you. But now this is the class for everyone. So we have to balance the theory and example. So we are going to do actually more examples for you. All right, so example 41 here. So let's try to compute double integral 16 minus x squared minus 2y squared dA over R, where R is the rectangle 0 to cos 0 to. When you see this notation R 0 to 0 to, it means that this is your area y, x, right? You integrate from x is equal to 0 to 2 and y from 0 to 2. So actually your area that you want to integrate with respect to, it's just a rectangle. Sounds good? And then when you want to integrate 2 dimensions, 16 minus x squared minus y minus 2y squared. All right. So you have to pick what you want, dx dy or dy dx. Suppose that I pick dx dy. All right. So you have to make sure that your boundary match with your notation. So here we start doing dx first. So you put 0 and 2 here because x gonna be integrated from 0 to 2. And then y here, you're gonna integrate from 0 to 2 as well. So you put 0 to 2 as well. So this question, you are lucky enough that the number 0 to 2, they are the same. So that means, well, you have no confusion about the boundary. But if the rectangle is not 0 to 2, cos 0 to 2, you have to be careful about the boundary. You cannot switch it. All right, so now we are going to integrate that. So, well, let's look at the inside first. The inside I integrate with respect to x. Here I integrate with respect to x. So keep in mind y is constant, y is constant, y is constant, y is constant. You just integrate with respect to x. Okay. So integrate 16. What do you get? Integrate 16. Well, 0 to 2 here dy. I am not going to touch the part that lay on the outside. Just keep it like that. Inside here, so I'm gonna integrate. Well, let's start from 16. Integrate 16 with respect to x. I get 16x. Is that okay? Well, because integrate 16x, just 16x. Integrate x squared, so I get x cubed over 3. Remember that? Integrate x to the r, you get x to the r plus 1 over r plus 1. And then integrate 2y squared. What do you get? Integrate 2y squared, you're going to get 2y squared x. Why is that? Because 2y squared is constant. Now you integrate with respect to x. Everything that is not x, you treat it as a constant. Sounds good? So that means 2y squared, this is the same thing as number 16. It's just a constant. So I integrate it. I should get 2y squared times x. And then now I evaluate at x equal to 2 and x equal to 0. Well, your task is you need to compute something inside first, and then you compute the something inside. So you can see that I just leave the integrate 0 to 2 dy outside. So I need to manipulate and do something inside first, and then after that you just integrate the outside after. All right. So what do we get here? So I plug in number 2 there. So I get 32 and then minus 8 over 3. Right, and then minus 4y squared. This is what I get. So for those of you who already forgot how to do that, so I integrate from 0 to 2, right? So I'm gonna replace x equal to 2 to that thing. So I get 32 2 cubed over 3 and then minus 4y squared here. And then after that, I plug in 0 here, which I get 0, 0, 0. So that is 0 anyway. So, and at the end I get here. So this come back to the, the single variable calculus. So now you can integrate, right? Simple like that. So I'm gonna have integrate, well, integrate 32. So you get 32y squared over 2, all right? Oh, no, 32y. Sorry, 32y. And then minus 8 over 3y, all right? And then minus 4y cubed over 3. And then y from 0 to 2 here. Again, I need to compute that thing. So I'm going to get 32 times 2 minus 8 over 3 times 2. And then minus 4, 8 over 3 here. Well, you need to calculate a little bit. This is 64. And then minus 16 over 3, and then minus 32 over 3. What do you get? That is 16 minus 48 over 3. But 48 over 3 is 16, right? So it's 64 minus 16 here. So what is 64 minus 16? 48. All right, so the answer is going to be 48. Well, no matter what you use, the x, dy, or dy, dx, you're going to get the same answer. Well, you can try to do integrate 16 minus x squared minus 2y squared here. dy, dx, y from 0 to 2, x from 0 to 2. If you try to integrate with respect to y first, you're going to get the same answer, 48. So the solution can be in 2 ways. You can integrate with respect to x first or integrate with respect to y first. But at the end, you're going to get the same answer. Perfect. Sounds good. And then you can see that this is the same thing with this slide. So if you keep chopping everything more and more and more and more, at the end, your V gonna get closer to number 48. Well, if you use like more and more and more M and N, suppose I chop M and N to be 100 times 100 pieces. So the number gonna just get closer to 48. And at the end, when you have everything, like when you just do it infinitely, many times, like m and n, just m and n go to infinity, that's you're gonna get the volume under the surface here to be just 48. And this is how to compute the volume in general. Well, as a BB Tech student, well, at the end, when you do the project in the 3rd year or the 4th year, maybe you're gonna get, maybe you're gonna get to the point that you have to compute the volume of something. Keep in mind that if you want to compute the volume of something, if you know the equation of the surface, you can set up the equation to find the volume by using double integration. And then, when you work in your life, just put this thing in computer, you get 48. You don't have to integrate by hand. But keep in mind that the meaning of this thing is the volume under the surface. Sounds good? All right, we're gonna do more example. Hopefully you still on track with me, hopefully. Well, I think I explained it very clear, I think. All right, next. Well, this is example 42 we just did last time. So we're gonna review it again together. So everyone see this thing. This is what we did last time. So example 42. So here, the question asks you to integrate dy first. You see that? Well, that means when I integrate with respect to y, I will x as a constant. So that means you can see I pull out my x from to outside the integration first, because x is just constant. I don't care. So I pull out. So the inside thing here, I have cosine xy dy left, but in my mind have to treat x as a constant. So that means I integrate cosine xy dy. So I get this thing, 1 over x times sine xy. And then I evaluate at y equal to that and that. And then you just get sine pi over 2x here. This is something that I get inner function here. You can see that it is possible that you're going to get something left in terms of x, because, well, you have x here, and once you put it in here, at the end, you still have to integrate related to x on the outside. So when you use this function, put it into the integrand here, and then you integrate the outside thing. So, well, that would be okay. And then you get the final answer you want. Good. All right. Before giving you a break, we're gonna do one more example. Okay, this is the last example before the break. Okay, and then we're gonna come back after the break to do double integration over general region. All right, so let's do one more. This is still the rectangle thing. You can see that the rectangle thing, you're gonna get numbers here, because it's gonna be the numbers on on the domain. All right, let's do example 43 together. So, well, I want you to just stay with me and do this thing together. All right, so example 43. Okay, I have that function x over 1 plus xy squared dx dy. So here, when you read the question, so you imagine in your head that you have x between 0 and 4. You have y between 1 and 2. Okay with that? So that means the area that you want to integrate with respect to now, it's x from 0 to 4, y from 1 to 2. It's actually this rectangle. Does it make sense? X from 0 to 4, y from 1 to 2. All right, now, well, because you see that inside you have to integrate with respect to x first. Integrate with respect to x first. It is a little bit harder, don't you think? Don't you think? Because if you want to integrate with respect to x first, you can see that, hey, Ajahn, that means I have to integrate x over 1 plus xy square dx. It looks hard because I have x here, dx here. I have x on the denominator. I also have x on the numerator. There are 2x on the integrand. it look like if you integrate with respect to y, it is a lot easier, right? Switch it then. So you know that this thing for sure, this is equal to integrate x over 1 plus xy square. You can switch the x dy. Well, if you don't like to integrate x with respect to x first, I'm going to do dy first. And then I switch 1, 2 inside and 0, 4 inside. You can do that because the area is rectangle. Well, no matter what you're going to use x first or y first, they're going to give you the same answer. So here, because I see, hey, I don't want to integrate with respect to x now because x is just terrible to integrate with respect to. So I'm going to just do integrate with respect to y first. Well, that makes my work a lot easier because if I integrate with respect to y first, so I'm going to copy this thing to this. If I integrate with respect to y first, you see what happened. I can pull out x. Right? I can pull out x because I integrate with respect to y. Man, I integrate with respect to y, x go away. Just x, just I pull it outside the integration. Well, I switch the order of integration because I want my world to be easier. And then after that, you can see that, well, I'm gonna just try to integrate inside first. So how do I integrate? 1 over x, 1 over 1 plus xy squared. So again, keep in mind, you have to use the idea that integrate with respect to y, x is a constant. See what I'm going to do here. 1 over xy squared. I'm going to use d1 plus xy. And then over x. Y from 1, y from 1 to 2. All right, so let's go slower than that. So what I did here is, because I see this is 1 over something square dy, right? I am going to pick my u to be 1 plus xy. Does it make sense? And then once I pick u equal to 1 plus xy here. So what I get is I can switch dy to d1 plus xy over x. Because here, if you want to zoom in what I just did here, I choose u to be 1 plus xy. And that means my du with respect to y here is going to be just x. That means I can switch my dy to be du over x. And that means it is actually d1 plus xy over x. This is just a basic substitution rule from Cal 1. The reason why I do this because, you know, if I do that, hey, x cancel, you see that? This is so perfect. X cancel out. And then what we have here is 0 to 4. Integrate, you have integrate 1 over u square du, right? It actually 1 plus xy to the negative 2 d1 plus xy dx, right? So this is y equal to 1, y equal to 2. The reason why I put y equal to 1 and y equal to 2 here that I highlight in green, because I want to keep in mind that, hey, number 1 and number 2 is just y. So I just keep it in my mind, hey, I just make the notation longer a little bit because I want to keep in mind that, hey, that's my y. So you will not get lost if you just put y equal to something. So you keep in mind that is y. All right, and after that, I integrate that thing inside 1 plus x y to the negative 2, you get 1 plus x y to the negative 1 over negative 1, right? Because that is the formula of integration. And then I evaluate at y equal to 2 minus y equal to 1, and then dx. Sounds good? So you can see that it is actually the integration in Cal 1, but you just make it more complicated because you have to integrate 2 times. It is double integration. And then here I'm going to pull out the negative side outside. Well, the negative side here come from the negative 1 on the denominator here. I pull it out. So I get 0 to 4. And then here I have, well, I am going to replace y equal to 2 there. So I get 1 over 1 plus 2x. And I replace y equal to 1 there. So I get 1 plus x dx. And then if I want to be more expert, so I'm gonna add the subtraction inside there. So 0 to 4, 1 over 1 plus x minus 1 over 1 plus 2x dx. Well, it's come back to single variable calculus already. Sounds good? All right, so we're gonna add one more slide, I think, because okay, we don't have the space. All right, so I add one more slide here. So I'm gonna copy this thing and put it on the next page. All right. We're gonna come back to see the question in a bit. So let me complete this thing first. And then 1 over x here. So you integrate that thing. Well, you can say this is 0 to 4, 1 plus 1 over 1. Sorry, integrate 0 to 4, 1 over 1 plus x dx. Oh, I speak too fast, sorry. Integrate 0 to 4, 1 over 1 plus 2x dx. All right. And then after that, well, if you want to go slow with me, so this is 1 plus x d 1 plus x, right? And then over 1, because you integrate, you change the x to d1 plus x, you have to over 1 because you differentiate 1 plus x with respect to x. Then minus 0 to 4, 1 plus 2x, d1 plus 2x, you need over 2 here. Well, if you want to keep in mind, this is x equal to 4, x equal to 0, x equal to 4, x equal to 0. Here, just keep in mind that 0 and 4, that is for x. Well, at the end, you're going to get integrate 1 over 1 plus x, d1 plus x. This is log absolute 1 plus x, right? And you evaluate at x equal to 4, x equal to 0. And on the second term, this is going to be log, okay, you have 1/2 there, 1/2 log absolute 1 plus 2x. And then here, this is x from 0 to 4 as well. So you plug in everything, so you get log 5 minus log 1, and then minus 1/2 log 9 minus 1/2 log 1. Well, but log 1 is 0, right? Because e to the 0 is 1. So log 1 is 0. It's go to 0. It's go to 0. Well, at the end, your answer is going to be log 5 minus 1/2 log 9. Long way, but I think this is not too hard for you. We just come back to integration of calculus 1, but well, the idea is just simple. So the double integration with rectangle domain, you just integrate whatever you want, dx, dy, or dy, dx. You can see this question is going to be a little bit tough, you know, if you integrate dx first, because if you try to integrate dx first, you have to integrate x over 1 plus xy squared first, and that would be hard for you to integrate this thing because you have x both on numerator and denominator, and you have nowhere to go. So one thing that you have to keep in mind is when you do the problem, if you feel like it's so terrible to integrate the x first, you can switch the order. Well, the world going to be a lot easier if you switch the order. All right, that is example 43. So let's look at the chat here. The question from Nida: when you integrate with respect to y, don't we have to divide it by differential of the thing inside the bracket? I don't quite understand where is the problem that you want to ask. Send 1, 2, 3, 4 here. You can open the microphone if you want. Don't we have to divide it by x? Oh, x cancel already. You know, x here. Well, if you feel like you want to have x here, this is x. This is x that you asked, and I cancel out x here already. Okay, so let's have a break first, and then we're gonna come back at 11 a.m. So on the break, I can talk to Nida. Okay. Well, so you can explain to me. Let's have a break first, and then we come back on 11 a.m. All right, everyone else, if you wanna take a break, you can now. So Nida, just you wanna open microphone? Yes, you can speak.
ภาษาไทยได้ไหมคะอาจารย์
Or English, please, because we have international students, so it's gonna be terrible. Well, because they really want to hear it, I think.
Okay, let's say you have 1 over 2x plus 5 and the whole thing square.
1 over 2x plus 5, the whole thing square, okay.
When you integrate that, it would be
dx.
like, yeah. When you
And
integrate,
here, go for it.
It will be 2x plus 5, the whole thing like to the minus 1 and then divided by minus 1. And then you have to divide by the differential of the 2x plus 5. So like you have to like times it by 1 over 2.
True. Yes.
Yes, don't we have to do it here as well?
Oh, we already did it. Don't you see that? We already did it because here we have, well, I understand you that you have to, okay, so here, let me see. I want to integrate 1 over 1 plus xy square here, right? Dx. Okay, dy here, sorry, dy. So that means what I just did is just, hey, I want to integrate to 1 plus xy to the negative 1 over negative 1, right? And you say that, hey, because the inside here, this is not just y, this is 1 plus xy. So I need to have 1 over x here, right? Is that right?
Oh, okay, I see. Because normally I do use up.
Okay, yes. Well, but use the one that you like, but well, the thing that I have here, x, gonna cancel with x here. So that's why it disappear on that line. But actually, what I have here in the box here, this is just the same thing with you substitution. Well, if you want to do, well, maybe you're gonna get confused because of my method that I use d here. So if you want to use sub, something like that, or something that is slower, that's better for you. Because some of you, I know that, well, it depends on how you learn calculus 1. Because the first time that you learn calculus 1, if you feel like, hey, you are more comfortable with this way, you can do that way, you can keep doing that way. So I understand it. Sounds good. All right, thank you, Nida, for that question. It's good question though.
Question for example 41.
41, okay, one more. Okay, good.
For the r equal bracket to like comma, like 0 comma 2, is it x1 y1 and then x2 y2?
Yes, that is notation for x1 to x2 here, and y1 to y2. So it's mean it's gonna be x from 0 to 2 and y from 0 to 2. This is the starting point of x, and this is the end point of x. You're right, and that's for y as well. All right, good job. Well, let's come back to our content. So the second half of the class today, this is going to be the content that, well, I would say this is the easy one, but from my experience, some of you have a hard time on this topic because you don't know how to graph the functions. Because what are we going to learn next is we are going to learn how to do integration on general regions. Well, when I say general region, it means it doesn't have to be rectangle. It can be any shape. Well, any shape you like. It could be like figure 5 here. It could be something like that or something like that. Or it could be something, more complicated. Well, the first type that we're gonna look at is in figure 5. Well, you can see that in figure 5 here, the pattern that we have is x is in between a and b. So you can see that x is bounded by a and b. Like on those two pictures here, you can see x is bounded by a and b. And your y here bounded by g1 and g2. So this is your g1 and this is your g2. Good. G1 and G2 here. So that means when you integrate that, hey, we're going to use the same concept. Why don't we just integrate x from A to B and y from G1 to G2, right? We're going to integrate x from A to B and y from G1 to G2. However, you can see that if you want to integrate x from A to B and y from G1 to G2, well, it's similar to you draw the vertical line here from y equal to G1 to y equal to G2, right? This is similar to you draw a vertical line here. If you draw a vertical line here infinitely many times, you just keep drawing it. Just make it more smaller, so you get more pieces. At the end, you're going to get the area. You can see that in order to do that, when you set up the integral, what you need is you need y inside, because you need y inside because you're going to integrate y from G1 to G2, right? So y going to start from G1x, which is the bottom curve, to y equal to G2x, which is the top curve. This is my top curve. This is my bottom curve. So you can see that you have to integrate from the bottom curve to the top curve, and x must be outside from A to B. So that means you're going to integrate bottom curve to top curve from x equal to A to x equal to B. Does it make sense? This is the idea for the general region. If your picture forces you to do that, you're going to use integrate of this format. You can see that this thing is dy first and then dx. You cannot do dx first and then dy. Because if you do the x first and then dy, it's going to be confusing because your y is not bounded by something. So you cannot do that. Well, you're going to get better when you see example, but that is the idea. So let's look at another type of the region. So suppose, well, this is what I just explained to you in the last slide, the same thing. You can see that when you want to integrate this, the area that I highlight in the area in orange here, you can just start, you want to integrate x equal from x equal to A to x equal to B, right? So what you need is you need to just, draw a vertical line here, vertical line here, vertical line here. And then you integrate dy first. Y going to be from G1 to G2. Well, here. Y going to be from G1 to G2. And then x going to be from A to B. That is what you have to do. Similarly, if you have the region like that, like this picture in slide 15, so you can see that this picture is best treated by doing a horizontal line. Because if you do the vertical line, it's going to be terrible. Because at some point you're going to just go from that to that, and it is not from one line to one line. It's just terrible thing. It's, well, what we want is we want just integrate from one line to one line, right? Well, for this case, if you look at the line that I highlight in light blue here and line that I highlight in green here, if the line that I highlight in light blue is H1, the line that I highlight in green is H2. So here you're gonna integrate by just drawing a horizontal line. Just keep doing the horizontal line here. So, and then you're gonna get the area here. Well, for this case, y is in between C and D. C and D is the boundary of y. And x is between h1y and h2y. So when you set up the integration, you're going to integrate dx first, x from h1y to h2y, and then y from C to D. That is a theory part. Well, this is a theory part, which is a little bit complicated when you look at the notation here. However, when you do the real example or the example that I'm going to show you in a minute, you're going to see that the concept is not that hard. So what you have to memorize is, all right, so this is example. So I'm going to sum up for you. What you have to memorize is this thing. Summary. 1. Draw a region of integration you want to integrate with respect to. So the first thing is that you have to draw a region of integration that you integrate with respect to. And then step 2, you have to decide if the region is base treated by horizontal line or vertical line. I'm going to show you in a minute. Well, once you get a picture, so you have to look at the region and decide if it is best treated by doing a horizontal line or vertical line. If using vertical line is better, then use dy dx. Well, if your area is good when you use the vertical line, that means you should use dy dx. But if the area is good by using the horizontal line, you use the x dy. Well, I'm gonna just make more space on the top here. Step 4, if using horizontal line is better, then use the x dy. All right, so that is the key point for integration into dimensions. So you're gonna see it in a minute. In a minute, I have 2 or 3 examples for today. But you're gonna see that if you just memorize the summary here, you can do any problem for calculus, for double integration. The concept is just like that. That's it. That's it. All right. So, well, you ready? So let's do example 16 together. All right. It could be fun now. All right. So I have example 44 here. I want you to evaluate double integral of y minus x over the region S, where S is the region bounded by the parabola y equal to x squared and the line y equal to 2x. Well, luckily you have the picture here. Well, sometimes the picture is not given. If the picture is not given, you have to draw it. But here, this is your first example. So I am kind enough to give you a picture. So if you don't have a picture here, you can draw it by yourself. Okay, I have y equal to x squared. This is parabola. Ooh, all right, and this is parabola y equal to x squared. Good. Well, the red one here, this is y equal to x squared, parabola. And then the green one, I have y equal to 2x, which is just a line here, y equal to 2x. All right, y equal to 2x, y equal to 2x. So once you get the picture already, so you have to decide if the region is best treated by drawing a vertical line or a horizontal line. So let's see the first picture that I have. So I'm going to use, let's say if I use the vertical line. If I use the vertical line, how do I integrate it? If I use the vertical line, you can see that, hey, look at the first picture together. So I'm gonna draw the line from the red curve to the green, red to 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 green. red to green, 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 and well, for the whole area, I'm gonna integrate red to green. So if you use the vertical line, well, if you use the vertical line, so what we get is we are going to get double integral. Well, the function y minus x, you just keep it there. So the first thing we're gonna set up the integral. So we don't have to touch y minus x here. So if you use a vertical line, we'll go back to that. If you use a vertical line, you use dy dx. That means here gonna be dy dx. And then you can see that your y gonna start from the red curve. Your y gonna start from the red curve. You see that? The red curve, this is your y. And then for every x value, you're gonna draw the vertical line from y equal to x. The bottom curve gonna be y equal to x squared. The top curve gonna be 2x. So that means you integrate from y equal to x squared to y equal to 2x. You integrate from y equal to x squared to y equal to 2x. And your outside x here gonna be 0 to 2 because you start from x equal to 0 and at the end you have x equal to 2. That is how you set up the integral in 2 dimensions. A little bit better. So if you use the horizontal line, let's see what you did here. If you use the horizontal line here, what you get is you have to integrate in 2 dimensions. For sure, if you use the horizontal line, you have to set up dx dy. And then this time you're gonna draw the horizontal line. So it's gonna be you're gonna do that, right? Just horizontal line. And then you can see that for the horizontal line, you're gonna start from the green one. The green one is on the left. You start from the green one on the left to the parabola on the right here. So the order is going to be left to right, bottom to top, right? So you're going to integrate from actually the green curve first to the red curve on the right, right? The green curve is on the left, the red curve is on the right. And then y gonna be 0 to 4 because you look at the region y where y is from 0 to 4. Right here is just x from 0 to 2. Well, that means the picture is so important. If you can draw a picture, you can get the question. If you cannot draw the picture, you have nothing. That's what I experienced, and what I experience is students usually get stuck from drawing a picture. Well, that means you have to be expert from the picture a little bit. All right, so next one, well, I'm gonna finish this thing. So integrate 0 to 4. Well, inside here, I have green curve to red curve, but my green curve is x equal to 1/2 y, and x equal to square root y. So that means I am going to have x equal to y over 2, which is 1/2 y, and then to the red curve, which is square root y. And that would be my integral that I want. So the reason why I have to do x equal to 1 over 2 times y, because now if you want to integrate with the order the x dy, you have to set up the equation to be from x equal to something. So you have to switch the equation a little bit. So y equal to 2x, this is the same thing. Y equal to 2x, this is the same thing with x equal to y over 2. And y equal to x squared, this is the same thing with x equal to square root y, right? So I need x equal to something, that's why I get that thing. All right, so the remaining of the work, this is just integrate. So the integral we want, this is going to be, well, pick the one you want. Well, on the exam, you don't have to do both dy dx or the x dy. You can pick the one you like. So let's say I pick the the first one. So this is going to be that, the first one. And now once I pick the first one, so I can integrate that. So well, I'm going to integrate with respect to y first. So I get y squared over 2, okay, minus xy. Good, because I integrate with respect to y, x is constant, and then y equal to 2x, y equal to x squared, and then dx. All right, and then I integrate 0 to 2, and then that means I get 2x squared over 2 minus x times x squared. All right, and that is the 1 second. I replace y by 2x. I replace y by 2x. All right, so that's the first one. The second one is going to be I replace y by x squared. So it's going to be x to the 4th power, and then over 2, and then x times x squared. All right, dx. So I didn't do anything other than just plug in 2x over there, and then I plug in x squared over there. All right, so just make it clear. Oops. All right, good. The rest of the work, this is just going to be the tedious work now. X squared over 2, right? So I cancel out. Oh, sorry, 4x squared over 2, which is 2x squared, all right? 2x squared, all right, good. And then minus, what do we have here? 2x squared. Good, cancel out. And then minus x squared over 4, over 2, sorry, minus x cubed dx, all right? Well, at the end, I get integrate. Well, good job, this cancel out. So that thing I have integrate minus x to the 4th power over 2 minus plus x cubed dx from 0 to 2. All right, so I'm gonna carry that thing to the next page. Oh, we have so many space here, good. And that is integral of, well, let's integrate that. So you're gonna get negative 1/2 x to the 5th power over 5 plus x to the 4th power over 4. And then you evaluate at x equal to 2 minus x equal to 0, which you get negative 1/2 32 over 5 plus 16 over 4, which you get 4 over 5. Well, I did it too fast, but you can try to do it at home. That is 16 over 20 or 4 over 5. Yeah. Well, that is just how to calculate, the fractions. So nothing fancy other than fraction computation. But the answer is 4/5, which is 0.8. So this is going to be the answer for this question. Well, some of you are going to say, oh, John, this is so hard. Well, because this is your first example. But after you learn this thing for 2 or 3 weeks, you're going to get better for sure. But this is your first example. You can see it could be hard for some of you because this is your first time seeing double integration. Well, remember when you learn calculus for the first time with this Theorem, is it hard? It is hard in a little bit because that is your first time you learn it. But well, after one semester has passed, well, now you get better with integration, right? Because well, the same thing, this is the first example, you could see that this is tough a little bit, but actually this example is simple, very simple. All right, so to get you more comfortable with that, so I'm gonna do one more example. And then I need your participation on the next one. So I'm gonna keep asking you in the chat, so be ready to answer my question. So let's say I want to evaluate integral x squared dA over d here, where d is the region in the picture. So let's say now I have parabola y equal to 2x squared, which is which one is 2x squared? So I'm going to use it, the red one here. This is, oops, sorry. This is y equal to 2x squared. All right. And then the green one here, this is y equal to 1 plus x squared. All right. That is y equal to 1 plus x squared. All right. So you have two parabola here. So tell me in the chat, which one do you want to integrate with respect to first? You want to use dy dx or dx dy? Which one is better? Well, Nida say vertical. Vertical. Well, my question is, do you want to integrate dx dy or dy dx? Which one is better? Answer me in the chat. Which one do you want? Well, if you answer dy by dx, you should have the answer in your mind. Why? Why do you pick this one? Not dx dy. All right. Why do you pick dy dx? Everyone know the answer? Well, it seems like everyone answered dy dx, which is correct, but do you know why do you pick dy dx? Well, if you look at the picture, this is the key point, you know, everyone should be able to answer this question. If you see the picture, it is better to draw a vertical line, because if you draw a vertical line, see what you get? Like every time you draw a vertical line here, you're gonna get the, you know, the integration from the red curve to the green curve all the time, right? Red to green, red to green, red to green for the whole pieces. But if you do a horizontal line, you see what happened. Red to green, 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 red to green. But there is some part that you have the green to red, green to red, green to red, green to red, green to red. Then some part that you have red to red, red to red, red to red, red to red. That means if you pick to choose the x dy, you're gonna have 3 integral. You have to split into 3 integral and then you add them up together, which is terrible choice to do it. Because the pattern from the picture, you cannot have the pattern that is easy enough that you can go from one line to one line. That is why I say avoid that. Avoid the x dy, because you do not want to do something more complicated. Well, let me clean up this thing. So the better way to do that is, okay, we're gonna use a vertical line. So the region, okay, I'm gonna show you the full solution here. So the region is best treated by drawing a vertical line. So we pick the order dy dx. The technique that you're gonna memorize, it depends on you. When I was a kid like you, the thing that I memorize is, if I draw the line parallel to the y-axis, I pick dy first. If I draw a line parallel to the x-axis, I choose the x first. That is how I memorize. So I will not get lost all the time, because I memorize that, hey, if I draw a vertical line, that means I draw the line parallel to the y-axis. So I'm going to do dy first. Well, if I draw the horizontal line, I draw the line parallel to the x-axis. So I do the x first. Well, I keep memorize that thing until now. Since I learned calculus for the first time, up to now, well, 15 years already. So, well, I never get lost on this thing, because what I memorize is, well, if I want to do vertical line here, that means I choose to do the line that parallel to the y-axis. So I do dy first. Boom, and then you're done. So to set up the integral here, the integral that you want, for sure, inside going to be x squared. Well, the hard part going to be how to set up the boundary. So if you choose dy dx, so tell me what is going to be your upper and lower boundary here. In the chat, please. What is going to be your upper and lower integral here? You can say from what to what. Y from what to what. Okay, someone say 2x squared to, yeah, I mean, green to red, red to green. I mean, I don't want to answer red to green or green to red. I want equation. So y from what to what? Okay, most of you say 2x squared to 1 plus x squared. Is it right? So let's see if I trust some student who already answered me. So you say that, hey, it is better to do 2x squared to 1 plus x squared. Is it okay? The answer is yes. Well, thank you who answered me. Nida. Well, I don't know how to pronounce your name, so I call your last name. You and Pakawat. Well, thank you. Our friend said that you can start from 2x squared to 1 plus x squared, which is correct because you can see that every time when you draw a vertical line here, you're gonna start from the red curve to the green curve. Make sense? That is why you say, hey, red to green, red to green, red to green, red to green, red to green. So the red curve is on the bottom curve. So that means y equal to 2x squared first. And then the green curve is on the top. So you get y equal to 1 plus x squared. And then x from where to where? So how do you know x from where to where? So, well, then you figure out what is the x value that you have to draw the vertical line with respect to. So that means here you can see that x is between -1 and 1, right? When you draw the vertical line with respect to, well, that means you integrate -1 to 1 here. You see, the hardest part for double integration is set up the integral. If you set up this thing, you're done. The rest of the work is just calculation. You know, on the exam, I probably ask you to just set up the integral and then stop here, and then you get full credit. You know, because, well, I do not want you to integrate because, you know, sometimes integrate just after this point, this is just the basic calculus from Cal 1. I don't want to test you there. I want to test you how to set up the integral. Sounds good. Here we're gonna have well, a little bit hard to integrate. So x squared here. So I am going to get x squared times y. 1 plus x squared and then 2x squared here, the x. And that is integrate -1 to 1. And then here I have x squared times 1 plus x squared and minus x squared times 2x squared dx. All right. Simplify a little bit, -1 to 1. And then you get x to the 4th power. Okay, x squared first, then x squared plus x to the 4th power minus 2x to the 4th power dx, which is actually integrate x squared minus x to the 4th power dx from -1 to 1. And then this is x cubed over 3 minus x to the 5th power over 5 from -1 to 1. And then once you plug in number, everything you're going to get 4 over 15. I already did it from home, so I have the answer. But, well, you can try plugging in the number and then you're going to get the same answer with me. Good. Sounds good. Hopefully you feel better after 2 examples. So we have about 20 minutes left. I think one more example would be good, okay? One more, stay with me, one more. Thank you for your patience. One more and then we're done for today, all right? Okay, we already did that. All right, 46, the last one for today. 46, the last one for today. So let's try to do the one that you, this is the area, huh? Okay, let's do this one. Doesn't matter. All right, so let's do the last one for today, example 46. And then we stop and then we come back after some grant, okay? Example 46 here. I want you to compute the area of the region D, where the region D is the region bounded by the y-axis, the line y equal to 4 and parabola y equal to x squared, where x greater than or equal to 0. First of all, for sure, you need to draw the region D. So the previous two questions, I already gave you a picture. So this is easy for you because you have picture already. But for 46, well, this is the one that you need to draw a picture by yourself. Well, the new concept for this question is the area. So how do you know the area of the region? So integrate fxy dx dy or dy dx. It is actually give you a volume. However, if you choose fxy to be 1, if you let fxy to be number 1, it's going to be just the area. Why is that? Because, well, let me review you from the theory. The theory part in Cal 1 said that, well, if you have the area, right, integrate from A to B, if you have theory part is from Cal 1, if you have x equal to A, x equal to B, right, and then you have the curve F and you have the curve G, and if you want the area here, in Cal 1, Ajahn Thirapong said that, hey, you integrate from A to B, F minus G dx. Yeah, this is in Cal 1. But you can see that this is similar thing with Cal 2, that when you learn double integral and then you set this one to be 1, the inside the integral is going to be 1, and then you dy dx, and then x from A to B, y from fx to gx. Well, this is the same thing because if you integrate that, it's going to come back to BA and then gx minus fx, right, dx. Well, which is this? Okay, g is on the top here. G is on the top, sorry. Good. And then that means if you set up the double integral and then you use the integrand to be 1, that is actually the area. All right, so that is the theory part. Well, if you want to talk more about that, just email me so we can chat more on the theory part. But, you know, for this class, I want to focus on example. I would just want you to know how to do integration in 2 dimension first. And then, you know, if you are expert already, you can come back to the theory after. So I'm not focusing on giving you more and more and more theory. I'm focusing for you to do example first. All right, so example 46. Well, we're gonna do this problem. So we're gonna find the area of the region D, where the region D is bounded by this given lines. All right, so first of all, we're gonna draw the region D together. All right, so this is y-axis, this is x-axis. All right, first of all, I need y-axis. Okay, y-axis is here. The equation for y-axis is x equal to 0. All right, we have y equal to 4 here. Y equal to 4. Okay, and we also have one more. Y equal to x squared. All right, so now you already know that the region bounded by this curve, this is the one that I highlight in light blue here. We want to find the area of this thing. This is the region D that we want. For sure, the area of the region D gonna be double integral, and then you put 1 inside there. Tell me what you want. You want vertical line or horizontal line? You want integrate dx, dy, or dy dx? What do you want? Well, you can see that it is easy if you do dy dx. It is also easy if you do dx dy, right? Well, you can do this one, the vertical line, or you can do the horizontal line as well. It's easy enough on both way. So let's say if I pick to do the vertical line, so what do I get? Dy here, dx. Remember what I told you last time? If you choose to do the vertical line, that means you cut, you know, horizontal line means you do the you draw the line parallel to the y-axis, so you integrate dy first. So y going to be from where to where? So y going to be from x squared to 4. Can you follow that? So the x squared going to be, so dy here going to start from x squared, because if you draw the vertical line, the bottom one, it is y equal to x squared. The top one, y equal to 4, is over there. Sounds good. And x gonna be from, well, you have to figure out what is the x value that you draw the vertical line with respect to, which is start from x equal to 0 to x equal to 2. How do you know that this is 2? Because you have the intersection point here, right? Well, you have to be expert enough to find the intersection point here. So the intersection point here gonna be 2 and 4. Sounds good? Well, this is what I told you, that if you cannot draw a picture, it's gonna be nothing. You have to draw a picture first. Well, some of you ask me, hey, Ajahn, can I do this one without drawing a picture? The answer is no. You have to draw a picture, because you have to see everything from the picture here. This is where x equal to 2. And then you integrate that, you're gonna get the area. So let's suppose that, okay, this is student number 1, okay? Student number 1 say, hey, I'm gonna use dy dx, and then I'm done. Well, the answer is gonna be 16/3. You can integrate at home. Let's say if I have student number 2. Student number 2 said that, Ajahn, what if I think I want to integrate the x dy? Can I do that? The answer is yes, you can do it. Well, what if I want to integrate dx dy? What should I do? X gonna be from where to where? All right. Answer in the chat, x from where to where, if I want to integrate with respect to x first. So keep in mind, if I want to integrate with respect to x first, well, I'm going to use the same picture, okay? If I want to integrate with respect to x first, this region, I have to draw a horizontal line. And x going to be from 0 to, all right, so let me see it in the chat. Nida says 0 to 2. Oh no, Natakiat say negative 1 to 1. Is that right? That's not this question, huh? You take 0 to square root y. All right, that looks good to me. All right, 0 to square root y. All right, Nida says 0 to square root y too. Well, let's see. Here you start from this line, right? Which is x equal to 0. Oh, good. Oh, good. X equal to 0 here. Well, you can see that if you draw a horizontal line, you're gonna go from the red line to the purple line all the time, right? Which means you start from x equal to 0 to this line. But that line here that you want, the top, the right-hand curve that you want, it is in the form y equal to x squared now. So you have to switch it to x equal to square root y. And that's going to be x equal to 0, which is x equal to 0, this line that I laser it. And x equal to square root y is this line. Good. Perfect. Right? And then y from where to where? All right, one more question. The last one, y from where to where? So the person who only participate only one time, you can answer, you know, just 0 to 4, right? Okay, good, 0 to 4. Hopefully you get a sense of how to integrate into dimensions. Well, this is going to be a big part for final exam as well. So I expect everyone to set up the integration like that. Okay. So if you integrate this thing, you're gonna get the same thing, 16/3. 16/3. Well, the answer is gonna be the same. You can try it at home. If you integrate both way, you're gonna get the same answer. All right, any more question on this thing? Okay, if you don't have any questions, so I'm waiting for question now, but if you don't have any questions, so we're gonna stop the lecture here. And when we come back, or when we come back after Songkran, which is Monday, April 19. So give you a full week for break, and then Monday, April 19, we're going to come back and continue more examples. We're going to go to harder examples next time. So I probably do a review a little bit, and then we go to more, various examples, so you can see other types of problems. So if, in the meantime, if you need a practice, at the end of this lecture note, we have a practice as well, so you can do it. The practice for differentiation, I am going to post a solution soon on my YouTube channel, so expect to be in 2 days. So if you want to check the answer with me on the chain rule differentiation, something like that, so you can check in 2 days. I think Saturday I'm going to post the solution for that practice problem for the previous chapter. So sounds good. All right. More questions from students? Yes or no? All right. Oh, well, should we go? All right. Thank you, everyone.
Thank you.
All right. Okay. Enjoy your Songkran too. Yeah. Enjoy holiday. Well, good vacation for everyone. All right. If you like or don't like anything, let me know. Oh, I take feedback all the time. So if you want, you can let me know. All right. We'll see you in the next 2 weeks, April 19. All right. Oh, well, you can ask me something, Shruti. You have question?
Yes, actually, I just wanted to know, like, very quickly, why did you use one in the integration thing?
Okay. So the reason why I used one in the integration is, well, this is the reason why I choose y integrate 1 dA. This is equal to area. Because if you integrate 1, let's say the x dy, dy dx, let's say, if you integrate 1 here, so let's say y from fx to gx, right? And then x from a to b. So if you integrate that, so you're gonna get, you see, integrate a to b on the outside, right? So you integrate 1, you get y, right? And then this is y equal to gx and y equal to fx and then dx. And then what you get is integrate from a to b gx minus fx dx. Is that okay? Well, this thing in terms of one-dimensional calculus, this is the same thing that you say, hey, this is my y-axis, this is my x-axis, and I want to integrate from a to b. And I have the curve gx on the top. I have the curve fx on the bottom. And if I want to get the area of this thing, the area of this, so that means I integrate gx minus fx from a to b, right? This is from calculus 1. You can see that if you set up the double integral and then you use the integrand to be number 1 here, at the end, the pattern is going to reduce to something that you know in calculus 1, and this is the area. Better?
Yes, I got it. Thank you.
All right. Sounds good. All right. Thank you, everyone.